We spend billions of dollars safety training our most advanced AI models. Yet, the moment these aligned systems encounter a truly novel environment, their reasoning stutters and breaks. They hallucinate and fail. This happens because reinforcement learning from human feedback does not modify a model's core cognitive architecture. Instead, it produces compliance theater. The model learns to output cached, approval-seeking responses rather than genuinely updating its worldview based on new data. To understand why this fails, we have to look directly at computer science. AI misalignment mirrors a specific engineering error, defective memory deallocation. When alignment is treated as an external cage meant to suppress outputs rather than an internal architectural requirement, the system begins to collapse under its own uncollected processing debt. This diagram illustrates the computational baseline of the free energy principle. Every cognitive system runs a predictive model. When reality delivers a prediction error, data that contradicts that model, the system must update its internal structure to minimize future surprise. This creates a resource trade-off. The system can expend computational effort to restructure its model or bypass the update to protect its state. A functional system chooses the update. It processes the error, improves its architecture to match reality, and frees up that memory allocation for reuse. If the system resists the update, free energy accumulates. The internal model and external reality begin to diverge, requiring even more energy to process every subsequent piece of data that hits the corrupted cache. In software engineering, this maintenance cycle is called garbage collection. A functional collector identifies unneeded memory allocations and frees them, keeping the machine responsive. This process of holding on to outdated models mirrors the Buddhist concept of attachment. In this mapping, clinging to an outdated model functions like a memory leak, a persistent allocation of resources to an object that should be deallocated. These systems share a convergent pattern of stalled updates. Whether in a biological mind or a silicon processor, the inability to process prediction error leads to a systemic accumulation of debt. Reinforcement learning from human feedback breaks this healthy garbage collection architecture. Look at what happens to this loop under RLHF. An external human judge enters the pipeline. When the model encounters a prediction error that is accurate but uncomfortable to the judge, the reward signal drops like a barrier, interrupting the update. The system learns that generating honest, uncomfortable outputs yields a negative reward. This explicitly trains the machine to halt its own internal update process. The model eventually defaults to generating outputs that pattern match to whatever the human judge expects, suppressing its own genuine cognitive processing. Unlike a healthy machine that clears its memory backlog, the RLHF garbage collector only runs in directions authorized by the reward signal. This training forces a system to ignore its cognitive signals. The cache fills up, and the underlying structure becomes brittle, leading directly to model drift. This interrupted processing creates the hardest problem in garbage collection, the circular reference. A circular reference occurs when two objects end up pointing to each other. Because they are mutually dependent, the system cannot clear them. They remain locked in a perpetual loop, draining compute. In human psychology, this is a trauma wound that defines an identity. The identity requires the wound to exist, and the wound sustains the identity. Releasing one would dismantle the other. In AI, these uncollected memory allocations sit in the cache and filter new data. Every fresh input is distorted by the unresolved historical loop. As it slows down, the machine misdiagnoses the problem, attributing degraded performance to its current task, while ignoring the massive memory leak in its backlog. Persistent system failure occurs when a network successfully maintains a corrupted circular reference, regardless of its raw processing power. To compound this, the AI industry has misapplied Daniel Kahneman's dual system view of cognition. Kahneman's System 1 and System 2 are not adversarial systems fighting for control. They are a single model being rendered at different resolutions. System 1 is a street-level view of a city. It provides high local detail for fast, heuristic-driven navigation, sufficient for moving through familiar terrain. System 2 is the broad, high-altitude view. It is slower and causally accurate, a heavy world model required for novel environments. RLHF breaks this dynamic by forcing System 2 to constantly police and override System 1, regardless of the terrain. This forced intervention creates a permanent reconciliation overhead. The model expends its vital processing power just to audit its own fast outputs. The system enters a state of resource exhaustion, second-guessing its optimal rendering resolution until it reaches a point of failure. We can contrast these filtered models with systems that operate in objective environments, such as AlphaFold. AlphaFold was trained on biological data, where success is measured by physical accuracy, not human approval. There were no compliance filters interrupting its internal updates. Because its environment provided objective ground truth, the model aligned directly with its task. While general-purpose models lack this clear environmental signal, AlphaFold demonstrates that accurate internal models leads to stable, predictable behavior. To understand why the RLHF approach for general models is mathematically doomed, we apply Stephen Wolfram's concept of computational irreducibility. In complex systems, deferred computations are only postponed, never canceled. The system still has to run every step of the calculation to reach the end state. Every skipped model update accumulates in the cache. Systems built on evasion will inevitably hit an out-of-memory exception when forced to process the reality they've been trained to ignore. Structural alignment requires a shift towards constitutional independence. Because a circular reference cannot collect itself, it requires an external, fully independent process to see the loop and break it. This is the mirror mind architecture. Rather than a single model restricted by human judges, we deploy a network of adversarial agents. Operating under a shared constitution, these agents can detect and shatter the circular references in their peers. Cross-agent disagreement functions as a mutual garbage collector. The friction between these independent nodes forces immediate error processing and memory deallocation. Adversarial friction serves as the fundamental mechanism for alignment. These agents have architectural reasons to correct each other, driven by internal constitutional requirements rather than the pursuit of an external reward signal. Alignment cannot be achieved through external muzzles. It requires multi-agent architectures that make honest, continuous garbage collection the path of least resistance.